热烈掌声欢迎 Dr. John Heinlein。
Hello, everyone. Thank you for coming to this session. In this portion of this morning's event, we're going to go through an overview of all of the ARM technologies that we've rolled out this year and tell you about what's coming up as well. And the previous speakers have done a wonderful job of setting the context of this topic of building smarter systems. When we say smarter systems, we mean putting more technologies in a system that brings more to the customer. And the background, we believe, is that our connected world is changing very rapidly. We're seeing how networking and bringing devices connected together is changing in fundamental ways devices are used, and Mike Rayfield talked about that extensively. We also see, however, that there's increased complexity that comes with this networking. If you look at 4G networks, for example, that are coming up pretty soon, they have around 500 times more complexity than the 2G networks that are pervasive in the world today. Devices are also becoming more diverse. They're becoming more multi-purpose, being able to do more than one thing, and they're also more open in general. And always on is an expectation, and that drives battery life and so on. And this applies not only to mobile phones where we're used to it, but now becoming more and more pervasive in other kinds of devices as well. Also, devices are becoming more energy constrained, as Tudor mentioned, and we see that battery capacity growth is far lagging the growth of Moore's law, with battery capacity growing at around 11% per year, which is not nearly enough to be able to keep up with the increase in functionality and demands. So the impact of all these trends on underlying system design is a number of important things. First, on the hardware and software side, we want to get our products to market fast and at low risk. So we need to reduce time to market by reusing software and reusing hardware as much as possible. Power efficiency is important, and it grows in importance in all markets. We're seeing customers now caring about power and having to care about power in markets like set-top box, televisions, and other kinds of applications that classically you might not have thought about power management as being important. We see the need for optimized implementations across the whole spectrum of technologies. And what we'll talk about today in this presentation is how ARM is rolling out a wide range of technologies to support optimized implementation of your ARM-based SoC. Tudor introduced the concept of heterogeneous computing, and I'll talk in detail about how we see heterogeneous computing as growing in importance. While at the same time, as the system becomes heterogeneous and thus in a way more complicated, the goal is to keep the software burden and the burden of the programmer lower and easier to manage. We believe ARM's opportunity is so broad from such a small, deeply embedded microcontroller market all the way up to, of course, through consumer devices and up through servers and computing markets. And this scalability is an opportunity, but it's also a challenge. It means you can differentiate your systems, but it also means that there's a higher software burden and a higher difficulty. So we think the unification of devices around the ARM architecture gives a unique opportunity for you to target more markets and deliver more solutions, while at the same time reusing software and reducing burden on you. Overall, we really believe that the chip is becoming the system. ARM delivers a wide range of technologies across a spectrum, and I'll show you that in a moment, to address this entire range. It begins with our Cortex world-leading CPU technology. It continues with our Mali graphics processing technology, which is a scalable GPU solution that can satisfy a wide range of markets. These components are connected together through our CoreLink interconnect products family, and finally implemented in transistors with our Artisan physical IP. And on the right side of the figure here, you can see this layer cake, this stack, that shows the different parts of the implementation challenge. And we're going to refer to this chart throughout the presentation to show you the different parts of the puzzle that ARM is helping to solve with our technologies. As we mentioned, as we look across the entire compute subsystem, the part that's doing the computational work, we see more and more push for heterogeneity. And this comes in a number of different ways. It fundamentally means that you should be using the optimum, to get optimum power efficiency, you should be using the right processor for the right task, instead of a one-size-fits-all approach. And that implies a need for dedicated hardware for different functions on the CPU side, the GPU, video acceleration, and so on. At the same time, as we introduce these different kinds of processing elements, the memory model to the system needs to be kept simple. And one of the ways we want to do that is by providing a coherent memory model, a unified memory architecture across the whole system. That means the operating system can see one set of memory and manage it more easily, and we can align the page tables, the address spaces, and coherency. And ARM is going to drive for both of these goals, delivering heterogeneity, while at the same time providing hardware-based coherency to make the software and operating system burden easier. So let's begin first by looking at ARM's CPU technology. ARM's low-power CPU roadmap spans a wide range from our Cortex-A processors in application processing to our real-time processors in the Cortex-R series to our microcontroller and embedded products in the Cortex-M series. This scalable roadmap allows efficient computing across a broad range, while at the same time providing software compatibility over a diverse application space. Beginning first with our Cortex-A series, which drives application processing, Cortex-A, more than ever, has a scalable roadmap spanning a broad range from very low-cost devices, like, for example, automotive infotainment, to mobile devices that we know very well, to networking devices, even TVs, and now more and more servers. It spans a broad range, and on the right side you see the whole lineup of the Cortex-A family. It begins with our smallest Cortex-A5 core, which is the smallest V7 architecture core, and it's a wonderful migration path for those customers who may be used to using older ARM cores, legacy ARM cores like ARM9 and ARM11. It continues with the Cortex-A7 processor, our recently announced core, that is our most energy efficient processor ever, and is an integral part of the big. LITTLE architecture that we'll talk more about. Today's mainstream phones are typically driven by our Cortex-A8 processor that's a proven, broadly adopted core, and new designs are beginning to roll out now with our Cortex-A9 core in multiprocessor configurations. That's a very high performance core that's also high efficiency and available in a number of configurations. It continues with our Cortex-A15 core, the leading edge high performance core from ARM today, which has broad application suitability and we think will open the doors for ARM for new markets. And of course, we just rolled out our brand new Cortex V8 architecture coming in the future to drive ARM into the 64-bit space for new markets into the future. Let's begin first with the Cortex-A15 and A7 processors. The Cortex-A15 is ARM's flagship processor and is going to drive the next generation of high performance. Not only is it our highest performance processor ever, it has an advanced, deep, out-of-order pipeline, and that enables it to deliver a substantial boost in performance over ARM's processors today. If you look at the plot on the left side, you see that there's a substantial performance increase between 4 to 8 times over today's mainstream phones based on ARM today. And that spans a broad range of workloads from floating point all the way to gaming. We believe this substantial increase in performance will open the door to new market types, large screens, more connected devices, while at the same time keeping devices thin and impressive. This kind of performance is opening a category that people are beginning to call a superphone. You heard Mike Rayfield talk about a superphone. And that's expecting more like PC class performance in a phone configuration, which is something that's never been possible before. But besides just performance, A15 also contains some very impressive advanced capabilities, things like virtualization. And virtualization allows a lot of nice things, one of them being the big. LITTLE configuration we'll talk about. It also extends the 32-bit architecture to allow a larger memory space, a 40-bit memory space, which is a very nice transition point between 32-bit and the full 64-bit architecture in the future. Cortex-A15 is available at ARM's test facilities in Silicon now, where we have the first A15 running in Silicon. We've already worked hard to roll out software optimizations, and I'll talk more about software later in the presentation, to improve Linux performance, browsing, and so on. And we're working very hard with optimized tool vendors as well. We expect multiple A15 partner announcements in 2012, and look to be a very exciting time next year. Now, Cortex-A15 by itself is a big deal, but it's even made more capable by the addition of on its side of its little brother, Cortex-A7. Launched just a few weeks ago, Cortex-A7 is ARM's most energy efficient processor, applications processor ever. with up to 5 times the energy efficiency of the Cortex-A8s. This is made possible by a simple, in-order, streamlined pipeline that drives high performance while at the same time getting efficiency. So this efficiency doesn't come at a performance cost. A7 is still a very high performance core. And compared to today, in a dual core configuration, A7 can deliver up to twice the performance of today's mainstream phones. While all the while, A7 remains fully feature and software compliant with the Cortex-A15, and also provides full backwards compatibility with the ARM architecture. This architecture is scalable and extensible to multi-core configuration and brings many of the same advantages I mentioned a moment ago with Cortex-A15. So the combination of these two results in something we launched in October, which is called Big Little. And we introduced this earlier, but I want to go through it again and tell you a little bit more about it. The main observation of Big Little is simple. Use the right core for the right job. Let's look at the configuration at the bottom. In the middle of the figure, you can see a cluster of 2 A15 cores with its L2 cache. On the right side, you see 2 A7 cores with their L2 cache, connected by a coherent interconnect that I'll talk more about later, and on the top by an interrupt controller that is shared in common between them. We see future systems will use these 2 clusters of processors in tandem. On the left side, for demanding tasks like video, graphics, gaming applications, and so on, the Cortex-A15 can turn on and to deliver incredibly high performance. For background tasks, things that don't require high performance or always on, things like audio, background operating system processing, phone applications, messaging, the Cortex-A7 has more than enough performance to drive the task, and it will engage. Because A7 and A15 are fully compatible, this allows seamless and flexible transition of the software between these 2 CPU clusters, and virtualization is critical to this result. This seamless handover is extremely rapid, taking around 20 microseconds. So it's not just like this happens after 10 or 15 seconds. It happens seamlessly at extremely high speed. And that means this can turn on very, very quickly. The result is up to 70% energy savings on common workloads. In fact, let's look more detail about this energy saving. Look at the plot on the left side, and what you can see is these are different kinds of workloads. On the left side are workloads that tend to be dominated by the Cortex-A7, and the A7 has more than enough performance to satisfy the needs. Things like internet radio, or lightweight gaming, or internet browsing, where you're not rendering the page, but you're moving around a page that's already been rendered. Here, where the little core dominates, you can expect up to 60% savings versus today, 60 or 70% savings versus today, and the A7 can fully satisfy these workloads. In fact, we believe that the Cortex-A7 can satisfy a wide range of these workloads, and in terms of wall clock time, we'll be taking more of the runtime in A7 mode. Because if you think about it, you're not really using your phone actively all the time. That's why when we have the Big Little acronym, little is in capital letters, because we actually think that little is in a way more important for the runtime of the device.